In the lecture today, we are starting a new subject. We are looking at context-free languages. Context-free languages are a generalization of regular languages. So every regular language is context-free, but not the other way around. There are languages that are context-free, but they are not regular. A grammar is called context-free if all production rules of the grammar are of this form. The left-hand side must be a variable. Now, the right-hand side can be any word containing variables or terminal symbols. There's no restriction on the number of variables that can be in the right-hand side. So if you recall, we have also discussed regular grammars, and regular grammars, basically right linear grammars, they had a restriction that in the right-hand side there was only a single variable, and for right linear grammars, this variable must appear at the outermost right of the right-hand side. For context-free grammars, there is no restriction on the right-hand side. So the only condition is that the left-hand side of all production rules is a single variable. Now, we call a language context-free if there exists a context-free grammar that generates the language. Context-free grammars and context-free languages are very important because they are used heavily to describe the syntax of programming languages, and they form the basis of parsing algorithms. So for most programming languages like Java, C, and so on, the syntax is described using a context-free grammar. And based on this grammar, there are parsing algorithms that parse these programming languages. Let's try to find a context-free grammar for this language. So how do the words in language look like? We have n a's followed by m b's followed by 2n c's. So we have to make sure that we have twice the amount of c's as we have a's. Now, how do we do this? We try to give a context-free grammar, and this grammar should make sure that we have twice the amount of c's as we have a's. So I think it's a natural idea that we try to produce the c's and the a's at the same time. So let's make a rule that produces 2 c's in the end and 1 a in the front. So we say that our starting variable can rewrite to a as cc. So we produce 1a and 2 c's at the same time, and our starting variable remains in the middle of the word. Now we can repeat this, we can apply this rule more often, so we can produce an arbitrary number of a's, and at the end of the word we will have twice the amount of c's. But at some point we have to produce these b's. Now, we cannot just add another rule that rewrites s to bs. Because if we would add a rule s goes to bs, then we could create a b, and after the b we could apply the first rule again and create an a that stands after a b, and that's not in the language that we want. So what we do is we say that, okay, we first have to generate all the a's and c's, and then we switch to a new variable. Let's say we switch to t, and this variable t will be responsible for generating the b's. Now t should generate an arbitrary number of b's. How do we do this? We say that t can rewrite to bt or to lambda. So it can generate an arbitrary amount of b's by applying this first rule. So if you want n b's, we apply the first rule n times, and afterwards the t removes itself by rewriting to lambda. Now let's do a slightly more challenging exercise. We are asked to show that this language is context-free. So we are asked to give a context-free grammar for this language. So what is this language? This language is the complement of, so it's all the words of sigma star that are not in this language here. So we're looking at the complement of this language. What are the words in this language? this is all the square words. It's all words that are of the form WW. So we are asked to give a context-free grammar for all the words that are not square words. So all the words that are not of the form WW for some W over sigma. Okay, so how do we do that? What shape do the words in our language L have? So first of all, if we have a word over sigma that has odd lengths, then clearly it is in L, because a word of odd length cannot be of the form WW. If we have a word of the form WW, a square word, then it must have even length. So words of odd length should be in L. Also words of even length are in L if they are not of the form WW. So how do we express that a word is not of the form WW? So if the word has even length, then it means that we can take it apart into two parts that have the same length. So our word W of even length can be taken apart into UV such that U and V have the same length. So U is the first half, V is the second half of the word W. And now we want to make sure that U and V are not the same, because if they would be the same, it would be of the form WW, it would be a square word. So how do we express that U and V are different from each other? They have to differ in at least one letter. So that means that if we look at the mth letter of U and the mth letter of V, then they have to be different for some index m. And here we are starting to count with 0, so m is an index between 0 and the length of U. So they have to have one letter at least different, and we say that m is the index of this letter where they differ. Now, if they differ in the letter m, then we can also write the shape of W in a different form. Namely, W then must be of this shape, it must be in this language. Now, this might take a short moment to digest. What do we have here, this language? It's actually the union of two languages. We start with sigma to the m. So this is m arbitrary letters, followed by an a, followed by sigma to the n, so n arbitrary letters. So we have some prefix m, then we have an a, and then we have a suffix of n arbitrary letters. And the second part here, so this first part is the word u. This is the word u. And the second part here is the word v. And the word v just looks similar to u. In the front we have m arbitrary letters, then a b, and then some suffix of n letters. So what this expresses is, this upper part here expresses that our word u is an arbitrary word that has at index m and a, and our word v is an arbitrary word that has at index m a b. So after m letters we have an a, after m letters here we have a b. So this is a different way of writing that u and v are arbitrary words that differ at position m. And the upper part here says that it differs by u having an a and v having a b. The lower part here says that we can also have that the index m of u is a b and the index m of v is an a. Okay, so our word w is in this language. If it's not a square word, it's in this language. Now, how do we show that this language can be generated by a context-free grammar? A trick is that since we have here sigma to the n and sigma to the m, if we swap them, if we swap sigma to the m and sigma to the n, then we have something that already looks much more context-free. So we have now just swapped sigma to the n and sigma to the m, so we get this form, and now it already looks very context-free because we have here an a in the middle and m arbitrary letters before and after the A. And here we have a B in the middle and n arbitrary letters before and after the B. So this we can generate by a context-free grammar. We can generate words that have an A in the middle and arbitrary letters left and right. And the same we can do with B. We can give a context-free grammar that generates words that have a B in the middle and arbitrary letters left and right. So let's try this. We introduce variable A. This variable A is responsible for generating words that have an A in the middle. The variable B is responsible for generating words that have a B in the middle. So how do we do this? We say that A can rewrite to XAX. X is an arbitrary letter, so X can rewrite to A or B. And so we can apply this rule an arbitrary number of times. We will produce a certain number of arbitrary letters left and the same number of arbitrary letters to the right. And we can finish by rewriting A to lowercase a. So in the end, we put the lowercase a in the middle. And we have the same amount of arbitrary letters left and right. And similar for B, we can produce the same amount of arbitrary letters left and right. And in the end, we put a lowercase b in the middle. So our variable A can generate words of this form. Our variable B can generate words of this form. So we can generate words of this upper part here by simply saying that our starting variable rewrites to AB. It's just a concatenation of a word in A with a word in B. And this lower part here is a word in B. We have a B in the middle, followed by a word in A. So we say that S rewrites to BA for this lower part here. So this is actually sufficient. This is a grammar that covers all the cases of words of even length, such that the word is not a square, not of the form WW. Now, we are still missing out on the words of odd length. So how do we make sure that S also generates all the words of odd length? We could add some fresh variables to take care of that, but the easiest way is if we just say that S is also allowed to rewrite just to A and just to B. Because A generates arbitrary words of odd length with an A in the middle, B generates arbitrary words of odd length with a B in the middle. So if we take A and B together, we get all possible words of odd length. So now we are done. We have a grammar that generates all odd words and all even words that are not squares. So we indeed have a grammar that generates our language L, the complement of all the squares. Now what about the language of squares? So the language that contains all the words of the form WW, where W is in sigma. And our alphabet sigma consists of letters AB. On the last slide, we've just shown that the complement of this language is context-free. So is L also context-free? And the answer to this question is no. L is not a context-free language. And we will later prove this using the pumping lemma for context-free languages. So there is a pumping lemma for regular languages that we've already seen, and we will see that there's also a pumping lemma for context-free languages, and we will later use this pumping lemma for context-free languages to show that this language is not context-free. But this is amazing because we have seen that the complement of this language is context-free, but the language itself is not. So this is a difference with the class of regular languages. This shows that the class of context-free languages is not closed under complement. So you can have a context-free language, and the complement of this language is possibly not context-free. And this is an important difference with the regular languages, where regular languages were closed under complements. The derivations in context-free grammars can be displayed nicely in the form of derivation trees. And we say that the grammar is ambiguous if there's two different derivation trees for the same word. So let's have a look at that. So let's say that we have a grammar G and we consider a derivation in G. So a derivation from the starting variable to some word W. And this word W does not need to be a terminal word, it could still contain variables. If the grammar G is linear, linear means that all the production rules of the grammar have at most a single variable in the right, then it follows that also the word W contains at most a single variable. Because in a linear grammar you replace one variable by some word that contains at most one variable. So anything that you derive contains at most one variable. In a context-free grammar, the production rules can have an arbitrary number of variables in the right-hand side. So that means also the word W that we have derived can contain multiple variables. And if we have multiple variables, then we have a choice what variable to replace. So strategies come into play. And two very basic strategies are leftmost or rightmost. And they do what the name suggests. In the leftmost strategy, we always replace the leftmost variable. And in the rightmost strategy, we always replace, unfold, the rightmost variable in the word. So let's have a look at a simple example. Here we have a grammar S can be rewritten to SAS or to B. We want to derive the word BAB. We start from our starting variable, we apply the first rule, so we rewrite S to SAS, and then in the word we have two variables, we have one S and another S, and now the strategy comes into play. If we are using a leftmost strategy, we are going to replace the leftmost S. So we replace this leftmost S by B. Now we have only one S, so we replace this S by another B, and we get BAB. If we are using a rightmost strategy, then the first step is the same, but now we have two variables, and we are replacing the rightmost variable, so we replace this S by B. Now we have only one variable, so no choice, we replace this S by B. So if we have derived a word with multiple variables, then there is a choice as to which variable we are going to replace. Now, actually, it does not really matter what variable we choose. What really matters is what rule we apply for which variable. So the result of our derivation does not really depend on the strategy. It only depends on what rules we choose for which variable. And this idea of the independence of the strategy is captured in the derivation trees. The derivation trees show what rule has been applied for which variable. On this slide we see a derivation tree for the grammar that we've seen on the last slide. So for the grammar where S can be replaced by SAS or by B. Now if you look at the leaves of this tree and you read these leaves from left to right, skipping possibly lambda, then the word you get is a word from the language generated by the grammar. So in this example, if we read the leaves from left to right, we get BAB. This BAB is a word generated by this grammar. Now formally, what is a derivation tree? A derivation tree has nodes that are labeled from variables, terminals, or possibly labeled with lambda. The root of the derivation tree always has the starting symbol of the variable as label. So this is where we start to derive. Here we have the starting symbol S. Now a node that is labeled with a variable has children that are labeled either with x1 up to xn if there's a rule that says that the variable that is the label of this node that we look at can rewrite to x1 up to xn, or if there is a rule that this variable can rewrite to lambda, so it's a lambda production rule, then the node labeled with A can have lambda as a single child. Now this might sound complicated, but it's actually quite simple. Here we have S, and this S has as children SAS from left to right, and these children are allowed because there is a rule S can rewrite to SAS. So these children are just the right-hand side of a production rule. Likewise, S is allowed to have just a single child B because there is a rule S rewrites to B. So if you look at a node in the derivation tree that is labeled with a variable, then the children read from left to right have to form a right-hand side of a production rule for the variable that is the parent of these children. So in this case the parent is S, and these children form the right-hand side of a rule for S. And likewise this B is the right-hand side for a rule from S. S can rewrite to B. And if we would, in this grammar we don't, if we would have a lambda rule, S rewrites to lambda, then we could also have that lambda is a child of a node labeled with S. Moreover, the leaves of this tree will always be labeled with terminal symbols or with lambda. So any node that is labeled with a terminal symbol does not have children, and any node that is labeled with a lambda also does not have children. So only nodes labeled with variables have children, and these children read from left to right form the right-hand side of a production rule. So intuitively these derivation trees are very easy to understand. You see that we started with S, and if you look at the children you see what rule we have applied. We have replaced S by SAS. Now this left S here we have replaced by B, and this right S we have replaced by B as well. So this derivation tree nicely captures what rule we have applied for which variable without taking into account the order in which we have to replace these variables. So it does not take into account whether we have first replaced this S or this S. And this is also good that this order is not taken into account, because we have seen that the order actually does not influence the result that we get. A grammar is called ambiguous if there are multiple derivation trees for the same word. So for instance, if you take this context-free grammar, S can rewrite to S plus S or to 0, then we can have different derivation trees for the verb 0 plus 0 plus 0. Let's have a look. This is a derivation tree for this word, and this is another derivation tree for the same word. Let's check that they are valid derivation trees. We have here S replaced by S plus S, and now we have replaced the left S by S plus S again, and we have replaced all these S's by 0. And indeed, if we read the leaves from left to right, we get 0 plus 0 plus 0. And here we basically have the same, but now we did not replace the left S, but we have replaced the right S by S plus S, and we have replaced the left S by 0. And also this tree, if we read the leaves, we get 0 plus 0 plus 0. So these are both derivation trees for the same word. This grammar is ambiguous. Consider the grammar shown on the slide. Is this grammar ambiguous? We have a rule that allows S to be replaced by S plus 0 or by 0. It turns out that this grammar is not ambiguous. So for every word in the language generated by this grammar, there's precisely one derivation tree. Not more than one. Otherwise the grammar would be ambiguous. So this grammar is not ambiguous, and surprisingly it has the same generated language as the ambiguous grammar that we've seen on the last slide. Both the ambiguous grammar as well as this non-ambiguous one give rise to the following language: 0 plus 0 to the power n, where n is greater or equal 0. So both generate the same language, and this shows that for some ambiguous grammars we can transform them into non-ambiguous grammars. The problem of ambiguous grammars has occurred also in a real-world programming language, namely in Algol 60, and there it became known as the Dangling else problem. So we have a grammar, and with this grammar we can derive the following. Namely, we can derive if some condition, then if some condition, then else. And now the question is, where does this else belong to? Does it belong to this if, or does it belong to this if? And it's not only that you might be confused, the language is really underspecified. The language allows for two different derivation trees for this word. So we can generate this in a way that the else belongs to this if, and we can generate the same word in such a way that the else belongs to this if. So this grammar is really ambiguous. There's two different derivations for this word, two different derivation trees. And if you want to read more about this, then you can look at a publication by Donald Knuth, The Remaining Trouble Spots in Algol 60. Ambiguity in grammars is typically unwanted, because we often use grammars to specify some programming language, and we would like to use the derivation trees in order to assign meaning to the words, to the programs. Now, if there are multiple derivation trees, like in the case of the Dangling else problem in Algol 60, then we may have different meanings that we can assign to the same program. And this is not what we want typically. On the other hand, these ambiguities are often resolved outside of the grammar. For instance, if you think of formulas, then such a formula like 0 plus 2 times 1, you may have a grammar that allows for two possible derivation trees, but then you can define outside of the grammar that certain grammar rules have precedence over other rules. And by defining such a precedence on the rules, you enforce that this is passed in a particular way. Namely that the 2 times 1 is passed as being together. Ambiguity is a property that is undecidable. So for context-free grammars, there cannot exist a program that takes a context-free grammar as input and tells whether the grammar is ambiguous or not. We will later indeed prove that this is impossible to write such a program. So ambiguity is an undecidable property. We have a few slides back seen an example of a language where we had an ambiguous grammar and a non-ambiguous grammar for the same language. A language is called inherently ambiguous if the language is context-free and if every grammar that defines this language is ambiguous. So a language is inherently ambiguous if it's impossible to find a non-ambiguous grammar for the language. One such example is this language. So we have words of the form a to the n, b to the m, c to the l. such that either we have the same amount of A's and B's, or we have the same amount of B's and C's. This language can be defined by a context-free grammar. One such grammar is given here. But there exists no non-ambiguous grammar for this language. So every grammar defining this language is necessarily ambiguous. So in particular, this grammar is ambiguous, and I leave it as an exercise to you to find 2 derivation trees for the word ABC. One of the main applications of context-free grammars is the definition of the syntax of programming languages. We have already discussed that the well-known Backus-Naur form is a particular notation for context-free grammars. Now we would like to use these grammars also to parse our programs. Parsing is the search of a derivation tree for a given input word. For context-free grammars, parsing can always be achieved in cubic time. What does this mean? It means that for every context-free grammar, parsing is possible in O of the length of the input word to the power 3 time. This big O notation roughly means that this is the number of steps needed to parse modulo some constant factor. So to be more precise, it means that for every context-free grammar G, there exists a parsing algorithm and a constant C, such that every input word can be parsed in at most C times the length of the input word to the power 3 steps. So this is roughly a cubic number of steps with respect to the length of the input word multiplied by some constant. And in this number of steps, the algorithm determines whether the word is in the language generated by the grammar, and if so, it also determines a derivation tree for this word.